Sodium hydrogen carbonate can be decomposed to form sodium carbonate, carbon dioxide, and water vapor. When 16.44 grams of sodium hydrogen carbonate is decomposed in a jar with no other gases present, an evacuated jar, that is 8.66 liters in volume at a temperature of 23 degrees Celsius, determine the following information. 1. What is the partial pressure of both carbon dioxide gas and water vapor in the jar after the decomposition is complete? 2. What is the total pressure in the jar after the decomposition is complete? 3. What is the mass of sodium carbonate remaining in the jar after the decomposition is complete? And 4. Does the data comply with the law of conservation of mass? Okay, so what we want to do first is balance the decomposition. And as we can see here, sodium hydrogen carbonate is NaHCO3. But we want to break it up into sodium carbonate, which is Na2CO3. Water vapor, which is simply water, as H2O. And carbon dioxide, which is CO2. In order to balance this equation, we need to put a 2 in front of the Na. And from there, we know that the total atomic mass of 2NaHCO3, if we refer to our periodic table, is 168.01. So in order to find the partial pressure, we need to first figure out how many grams of CO2 and H2O we have. And to do that, we need to just simply find the atomic mass of CO2, which you could refer to your periodic table. And CO2 has carbon, so we'll go to CO2, which is here, and oxygen, which is here. And we simply add carbon, which is 12.011, to oxygen, which is 15.99, plus another oxygen, which is 15.99. And in doing so, we can find the atomic mass of carbon dioxide, which is 44.01. And then we divide by 168.013, which is what we got from right here. And in doing that, we get 0.26, which simply refers to as 26% carbon dioxide. And then after that, in order to find the grams, we multiply 0.26 by 16.44, which is the amount of grams that they gave us at the beginning. And in doing that, we get 4.27 grams of carbon dioxide. We do that to all of the other ones, which is water. In this case, water is 18.02, and we divide it by 168.013. We get 0.11, which is 11%. 11% water vapor, and then we multiply it by 16.44 and get 181 grams of water vapor. And then we do the same thing for sodium carbonate. In this case, it's 105.99 divided by 168.013. In doing that, we get 0.63, which just simply translates into 63%. And we do the same, multiplying 0.63 by 16.44 and get 10.36 grams. It's important to keep in mind that your percentages, so in our case it was 26, 11, and 63, should add up to 100%. And your grams, which in our case were 4.27, 1.81, and 10.36, should add up to 16.44. So by doing this, we can then go on to solve for partial pressure. The ideal gas law is PV equals nRT. And in our case, we're looking for pressure. So we'll use P equals nRT divided by V. So in using carbon dioxide as an example, the partial pressure of carbon dioxide equals 4.27 grams, which is N, times the numerical values of the gas constant R. In our case, we're going to be using atmospheres. So we're going to be using 0.08206 times 296. We got 296 because that is the temperature, which is T. In our problem, it gave us in Celsius, 23 degrees Celsius, and we simply convert that to Kelvin by adding 273 to it. So 273 plus 23 is 296, all divided by V, which in our case was 8.66 given to us in the problem, and we got 11.9 atmospheres, not 11.98 atmospheres of carbon dioxide. We do the same process for H2O and Na2CO3, and that's the solution to the first problem, or the first question. 11.98 atmospheres of carbon dioxide and 5.08 atmospheres of H2O, water vapor. In order to find the total pressure, we need to simply add all the partial pressures together. So we'll take the 11.98 atmospheres that we got from carbon dioxide, add it to the 5.08 atoms of water, and add it to the 29.06 atmospheres of Na2CO3, and we get a total pressure of 46.12 atmospheres. For the last question, does the data comply with the law of conservation of mass? We just need to simply go back up to the top and look over here. So here we had 168.01, and in order for this to comply with the law of conservation of mass, this needs to equal this, and vice versa. So whenever we add up 105.99 to 18.02 to 44.01, it should, if it's going to comply with the law of conservation of mass, add up to 168.1.01, which here it clearly does. There's just a little bit of rounding error, but it should be around there, and it is. So yes, this data does comply with the law of conservation of mass.